In this video, we'll walk you through a demonstration of using Fluent's Materials Processing Workspace, a workspace designed to model non-Newtonian fluids such as extrusion, blow molding, and so on, using a wide range of generalized Newtonian models, simplified viscoelastic models, and full differential viscoelastic models. The workspace is available as a beta feature in the Fluent launcher when using the enterprise licensing. We'll select the Show Beta Launcher Options checkbox. Choose the Materials Processing Workspace, and click Start. For this video, we'll briefly walk you through the use of a basic extrusion template, where we'll calculate the shape of the die that will produce and extrude it with the desired cross-section. In the Setup properties, under Read, we'll click the Polyflow Mesh button. We'll locate and select a 3D extrusion mesh. In the ribbon, we'll choose Use Template to display the Simulation Templates dialog. Set the type to Extrusion, set the goal to be Determine Die Lip Shape, and click Apply. This will instruct the workspace to set up the appropriate objects and settings based on our selections. Notice the outline view's use of status icons. A green check mark indicates the properties of that object are satisfactory. A red X indicates that attention is required for that object. We can progress down the outline view or across the ribbon to complete our simulation settings using each object's property pages. Rather than use the default fluid, we'll import a material from the library using the ribbon. In the Library of Materials dialog, for Family, we'll select Extrusion. For Material, we'll use the material called Extrusion Filled Rubber Isothermal 373K. And click OK. We'll delete the original fluid material using the context menu, and we'll edit the newly imported material by selecting it in the tree and exposing its properties. For View Properties, we can select the viscosity law and review its properties. Next, we'll define the fluid cell zone condition. Under Cell Zones, select Fluid Zone in the outline view. For zones, click the field to open a selection dialog, where we'll select both die and extrude it, since the fluid flows through each zone. Similarly, for the fluid materials, we'll select the imported material. Next, we'll start defining the various fluid boundary conditions. First, the extruded exit. For the boundary zone, we'll select Exit. As for the free surface boundary condition, for boundary zone, select Free Surface. Note how the selected boundary is highlighted in the graphics window. For fixed part, select Wall, since it's the boundary to which the free surface is attached or starts, and where its position is fixed. For the inlet boundary condition, we'll select Inlet for the boundary zone. For the flow specification, we'll choose Volume Flow. For the incoming material, we'll select the imported material and enter a value for the volume flow. For the wall boundary condition, we'll assign the wall for the boundary zone. Since the mesh we read into the workspace represents only a quarter of the full die, we'll need to add two symmetry boundary conditions. Click the Fluid Boundary Conditions in the outline view and select New. Change the type to Symmetry and change its name. For the boundary zone, we'll make the necessary selections. Perform the same operation to create another symmetry boundary condition called Symmetry 2. For the boundary zone, we'll again make the necessary selections. Finally, we'll address the mesh deformation. In this case, we want to keep a parallel die, one with a constant cross-section, so we do not need the adaptive dissection. So we'll delete the adaptive dissection object and address the constant dissection. For zones, we'll select die. For the inlet section, we'll select Inlet. And for the outlet section, we'll select Extruded Die. For the extruded, for zones, we'll select Extruded. For the inlet section, we'll select the die lip, designated as Extruded Die. And for the outlet section, we'll select Exit. Notice that the state indicators now are all green. Now we can progress to solution settings. Solution settings use reasonable defaults that will be adequate for most problems. This area is primarily used for checking the simulation setup and performing the calculations. For this video, we'll need to visit Convergence Strategies. Enable free surface and moving interfaces. This convergence strategy is needed to handle the nonlinearities related to the calculation of the free surface location. Since the free surface will deform, the mesh in the extruded must be adapted. Enable viscosity and slip. This convergence strategy is needed to handle the nonlinear viscosity model. Once the setup is complete, we can proceed to starting the calculations using the Run Calculation portion of the Solution node. Click Calculate. The setup will be checked prior to starting the calculations. A progress bar displays the progress of the calculations. Once the calculations are complete, we can check the listings file to verify our solution. We can view the listings in the transcript window. When we have a complete solution, we can go to the Results section to investigate the mesh, add contour plots, vector plots, and so on. The Workspace also allows us to analyze time-dependent or transient results. Given the symmetric attributes of the original mesh, we can create mirror planes to display a more complete representation of the original geometry. We can access mirror planes through the ribbon. In the Mirror Plane dialog, we'll select X and Y and close the dialog. Just as in Fluent, we can create our own graphics objects manually. For instance, we'll select Contour and New. For Field, we'll select Velocities. And for Surfaces, we'll select Extruded Die, clicking Display to update the graphics window. We can use the Quick View menu in the Results ribbon to quickly display velocity, pressure, and temperature contours for the fluid zone. First, we'll show the variation of velocity along the planes of symmetry. Note the new section of the die that has been adapted to compensate for the deformation of the extrudate that mainly comes from the rearrangement of the velocity profile at the die exit. We can also use the Quick View menu to display pressure contours for the fluid zone. Note that a pressure drop can be observed in the die, while the pressure in the extrudate is constant because the free surface is at atmospheric pressure. In conclusion, the Materials Processing Workspace provides a means to easily model non-Newtonian fluid problems such as extrusion or blow molding within the Fluent environment. This concludes this demonstration of using the Materials Processing Workspace in ANSYS Fluent. Thanks for watching.